Welcome back. Quadratics and factoring. I'm going to continue this topic and I'm going to cover perfect squares in quadratics, or just actually in polynomials in general. And I'll give you a few examples and what to watch out for and how to actually factor these perfect squares out if they are a perfect square. Now, if you go back into elementary school, then you may recall that these perfect squares basically were just numbers, and typically just whole numbers that you would have. So for instance, 4 was a perfect square because 4 was simply 2 times 2. And the reason why we say this is a perfect square is because if you look at a square, right, and it is a perfect square, meaning all the sides are the same, then you would notice that if this side was 2 and this side was 2, then your area, your overall area, would have been 4 because it's just simply 2 times 2. And that's what makes 4 a perfect square, because it is made up of 2 squared. Now, of course, there are many other perfect squares. So 9 was a perfect square because it was 3 squared. 16 was a perfect square because of the fact that it is 4 squared. 25 was a perfect square because it is 5 squared, and so on and so on. And the main idea is if you take a number and you take, for instance, the square root of the number, then you're going to get exactly your base back. So for instance, if I took the square root of 4, all right, then what we would get back is really just 2. And 2 squared would have given us 4 back. If I would have taken the square root of 9, you'll notice that it's going to, of course, give you 3. And if you take the square root of 16, it's going to give you 4, and so on. And you can go back and forth between these perfect squares and then the actual length of a side of an actual square itself. And then you can think of the areas as relating back to your perfect squares. Now, if you're taking quadratics and you start talking about polynomials, you're not going to be just having numbers. I mean, numbers are great to work with. They're definitely much easier. But if you start introducing variables like x and y and z or a and b, it doesn't really matter, then you can change these perfect squares by using and introducing these variables. So for instance, instead of having a number, what I could put is I could simply say, all right, what if we had x plus 2 as the length of our side? And if I wanted to make a perfect square, then the other lengths would also have to be x plus 2. And that means that the area, so the overall area, would have been x times 2 squared, and I would get a perfect square out. Now, my perfect square is no longer going to be a number. It's going to be an expression in this case. Now, I can expand this out. If I take this and I expand it out. Now, there's a very easy way to expand this if it is simply a perfect square. Of course, the square just means that we're multiplying it 2 times. So you can use the distributive property. So x, of course, is going to be x times x, which is x squared. It's going to give us then, and then so on. So I'm going to get 2x plus 2x plus 4. And combining my like terms, which is going to be x squared plus 4x plus 4. This entire expression, it is not a number anymore, but it is called a perfect square. And in this case, it's a quadratic perfect square. And you can get this back right here if you factor it out. And now, how do you notice if it is a perfect square or not? We should remember, how to actually factor these quadratics if you've watched my past videos on this topic. Okay, so I'll put up a link up above if you forgot about the quadratics in general. Now, that strategy will work. We can use factoring in exactly the same way. And for these quadratics, which kind of had the form of a times x squared plus b times x plus c, what we would do is we would kind of multiply the outer numbers together. So in this case, notice that I have x squared and then I have 4 at the end. And if I wanted to factor this out, then what I would do is I would say, okay, well, the a is equal to 1 in front, So that a right here is just equal to 1. And I have a 4 at the end. So 4, well, which two numbers make up 4? Well, actually, it's 2, right? 2 times 2. And then 2 plus 2 is going to give me 4 back in here. And so therefore, I know that this factored out is just that, which is showing me that indeed that expression is a perfect square. Those are perfect squares when you're considering expressions. Now, is there an easier way to be able to see these perfect squares? And it turns out there is. And if you're going to tackle these perfect squares and these actual quadratics or any polynomials, then what I encourage you to do is, instead of looking at anything, simply take your first, okay, so your leading highest order, okay, term. In this case, the order is 2 because it's a quadratic. And then you're going to take your last one. This way it's 4. If you take the square root of those, so if I'm going to take the square root of those two, so if I would have done this and I would have done this, then what do I get? Well, from here, what I get is if I take the square root, I'm just going to get x. If I take the square root of this, what I'm going to get is 2. And notice this is exactly what you get right here. So now, if that happens, right, that you actually can take the square root and it gives you, okay, direct expressions back or direct factors of that back because they're squareable, then you're going to take those two, so x plus 2, and then you can check for yourself, all right, if I square this, then what is going to happen to my middle number? This number is 4x. And notice that if I expand this out, as I did, then my middle number is also going to be 4. And the reason is because it is 2 times x, and then I have 2 of them, so that middle, okay, is going to be 4x. And you have just found your square root. Let's try a few examples with these perfect squares and then how we can try to see how to do them. So here are a few. Now, if I take this, my question is, all right, is this a perfect square? Right? If I factor this out, if the two factors are identical. So again, so what you do is you're going to say, okay, I'm going to try this. So I'm going to take this and I'm going to take that. If I take the square root of that, what will I get? Well, the square root of 9 is 3. The square root of x squared is x. That's the first one. If I take 16 and I take the square root of that, then what I'm going to get is 4. Now, the sign that you have that goes in between them is going to be the sign that is actually in that middle term. So that middle term is a plus. So I'm going to put a plus here, right there. So that's what this is. And now I have to check, if I square this, am I going to get, if my middle number is indeed going to be 24. And the way that I do that is because I'm squaring, so that means there's 2 of them. And what I have is I'm going to take, so 3 times 4, which is 12. And I have 2 of those. So times 2, which is going to give me 24. And that aligns with this. So indeed, it is a perfect square. And again, a reminder, what does it mean to be a perfect square? It means that it's literally just a square. So if I do that, so here's my square, and it would have been that all the sides, in this case, in my square, would have been that. So if I multiply them, I'm going to get this expression back. And you can double check for yourself if you expand this out, if it actually brings you back to this. And you'll see that it will. The second example that we have, so if I take the second example here now, so if I take, my test is always going to be, take the square root of these. And now my square root of 4y squared, that's going to be 2y. And now the square root of 1 is just 1. The sign that I take is always going to be the sign which is there in the middle. I'm going to put a minus in here. And now I'm going to check, okay, if I square this, do I get that 4y right here in the middle? That's my checking point. So how I do that is I'll just say 2 times 1. That's 2. Now there's going to be 2 of them because I'm squaring. So this is going to be that. So it gives me 4. And notice that it will be negative because 2 times negative 1 is actually negative 2. So this indeed is another perfect square. So I have found my perfect square right there, and those are my factors. And now the last one, this is not a quadratic because it has x to the 4, and also the middle term is x squared y. So I'm going to check if I can actually find a perfect square for this. Now, even though this is much more complicated, you're still going to do the same thing. You're going to take this and you're going to check, all right, can I take the square root of that and does it give me something in return? And in this case, so square root of 25 is 5. Square root of x to the 4th is x squared. This is going to be x squared right there. So that's my first one. Now I go to my last one, and that last one is, in this case, it's y squared and y squared. So take the square root of that, it's just y. My sign that goes in between, so it's going to be that sign right there. So that's going to be a plus. And now I'm going to check. All right, so if I square this, now what will happen? Am I going to get this middle term back? And indeed, so notice if I multiply this times this, I'm going to get 5x squared y. And there's going to be 2 of them. So 2 times 5x squared y, which is just 10x squared y. And it's positive. And that is indeed the middle term. So that is the factoring out of my perfect square of that expression. Now, what I would want you to know is, because sometimes the question is, why when you're doing the middle term, you're just multiplying these two and then finding out what that is and then multiplying it by 2. And the reason is because of the fact that that is exactly what you're doing, okay, because you're doing it 2 times. And where it comes from is right here. So because you want to find the middle term, so the middle term, so this times this gives you the first term. This times that gives you your last term. But your middle term is always going to be your second, so this times your first. So that's why I'm multiplying these. And notice I'm going to get 5x squared y from there. And then, okay, your second one that you have is going to be, okay, so this right here, so this times that. And that is also 5x squared y. And that's why you have 2 of them. And that is your middle term that you have there. That's how you factor out these perfect squares. Now be careful because they're not always perfect squares. So if you don't notice this pattern that you can take a square root of this and a square root of this, okay, then you have to now go back, okay, and try some of the other techniques in terms of factoring out. But if it is squareable, so if it is possible to take the square root, then you do it, and then you check if it matches up with the middle term. And then if it does, you got a perfect square. All right, so thanks for watching, and we'll see you in a future video. Bye, everyone.